Welcome to True Projects. In this video, we are going to explain about the project title Lightweight EfficientNetB3 model based on Depthwise Separable Convolutions for enhancing classification of leukemia white blood cell images. Introduction. Leukemia is a form of blood cancer that specifically impacts white blood cells. It results in abnormal cell growth primarily occurring in the bone marrow. If undetected or untreated, leukemia can lead to severe complications due to the abnormal production and behavior of these cells within the bloodstream. Acute lymphoblastic leukemia stands out as the most prevalent form of leukemia in children, but it can also affect adults. This particular type of leukemia involves the rapid production of immature lymphocytes, a type of white blood cell in the bone marrow. Diagnosing leukemia involves the classification of white blood cells within the bone marrow. This process encounters challenges due to the similarities between cancerous and normal cells. Distinguishing between the two types accurately is crucial for an accurate diagnosis. The project aims to improve the classification of leukemia cells by leveraging a specialized approach. Specifically, it focuses on utilizing a lightweight EfficientNetB3 model that incorporates depthwise separable convolutions. This methodology is expected to enhance the accuracy and efficiency of identifying and distinguishing between cancerous and normal white blood cells, potentially aiding in more precise leukemia diagnosis. Objective. The primary aim of this project is to refine the classification process specifically for acute lymphoblastic leukemia cells. It intends to achieve this by employing an innovative approach utilizing a lightweight EfficientNetB3 model. This model is structured based on depthwise separable convolutions, which are designed to enhance accuracy and efficiency in identifying ALL cells within white blood cell images. The broader goal here is to create a computer-aided system that demonstrates high accuracy in precisely classifying leukemia cells found in images of white blood cells. By achieving accurate classification, the project seeks to significantly improve the diagnosis of ALL. This improvement in diagnosis is crucial for effective treatment strategies, ultimately contributing to improved survival rates among individuals affected by ALL. Existing machine learning and deep learning classifiers often encounter challenges related to poor generalization, inability to perform well on unseen data, and slow convergence, taking longer to reach optimal performance. The proposed model, designed around the EfficientNetB3 architecture with depthwise separable convolutions, aim to tackle these issues. It endeavors to enhance generalization, allowing for better performance on new unseen data and improve convergence speed, making the learning process more efficient. To validate the effectiveness of the proposed model, the project plans to conduct a comprehensive evaluation. This evaluation involves comparing the performance of the developed model against established classifiers. Metrics such as accuracy, precision, recall, and FN score will be utilized. These metrics help gauge different aspects of the model's performance, from overall correctness, accuracy, to trade-offs between precision, exactness, and recall completeness of the model's predictions, providing a comprehensive assessment of its capabilities. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8GB and above, hard disk of 25GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3. Front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This step involves importing necessary libraries and packages in Python, such as TensorFlow, Keras, or other image processing libraries. These packages provide tools and functionalities required for data handling, model development, and image processing tasks. Exploring the dataset. CNMC-LU dataset. This dataset contains images related to leukemia white blood cell detection. Exploring this dataset involves understanding its structure, size, image format, and labeling, which are crucial for training machine learning models. CNMC-LU detection from RoboFlow. RoboFlow is a platform that provides datasets for computer vision tasks. The dataset labeled CNMC-LU detection likely refers to a version or subset of the original dataset prepared or processed using RoboFlow for the detection task. Image processing. Using Image Data Generator. This is a tool in Keras used for image augmentation and pre-processing. It generates batches of augmented images during the model training process, applying various transformations to increase the diversity of the training dataset. Rescaling the image. Rescaling involves normalizing pixel values to a specific range, commonly between 0 and 1, to ensure uniformity in data representation. Shear transformation. Shear transformation involves tilting or skewing the image along its axis, introducing variations in the dataset to enhance model robustness. Zooming the image. Zooming alters the scale of the image, magnifying or reducing specific regions, contributing to the model's ability to recognize features at different scales. Horizontal flip. This transformation flips the image horizontally, adding mirrored versions of the images to the dataset, further diversifying the training data. Reshaping the image. Reshaping involves altering the dimensions of the image, typically to match the input size required by the neural network architecture. Building the model. This step involves creating the architecture of the machine learning model. For this project, it's based on the lightweight EfficientNetB3 model utilizing Depthwise separable convolutions. The model's layers, connections, activation functions, and other architectural components are defined in this phase. Training the model. Once the model architecture is established, it needs to be trained using the prepared dataset. Training involves feeding the model with labeled data, adjusting its internal parameters, weights, and optimizing these parameters to make accurate predictions. The model learns patterns and features within the data during this phase. Flask framework with SQLite for sign-up and sign-in. Flask is a web framework used here to create a web application. SQLite is a lightweight relational database used for user authentication, sign-up and sign-in functionalities. These components together create a user authentication system allowing users to register and log into the application. User upload an image for analysis. Within the web application, users have the capability to upload an image for analysis. This uploaded image serves as the input data for the subsequent analysis process. The given input is pre-processed. The uploaded image undergoes pre-processing steps before being fed into the trained model. Pre-processing involves resizing, normalization, or any other required transformations to ensure the input matches the format expected by the model. The trained model is used for predicting the result. The pre-processed input is passed through the trained lightweight EfficientNetB3 model. The model applies learned patterns and features to predict whether the uploaded image contains leukemia white blood cells or not. Final outcome is displayed. The prediction or analysis results generated by the model is then displayed to the user within the application. This outcome includes information such as the likelihood of leukemia presence in the image or a classification label indicating the presence or absence of leukemia cells. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm is VGG19. VGG19 is a deep convolutional neural network known for its deep architecture with 19 layers. It's characterized by its simplicity and uniform architecture comprising multiple convolutional layers followed by max pooling layers and fully connected layers. While effective, it might have a higher computational cost due to its depth. Exception. Exception is an extension of the inception architecture but replaces standard convolutional layers with depthwise separable convolutions. This architecture aims to capture both spatial and channel-wise dependencies efficiently, potentially enhancing feature extraction and reducing computational complexity. ResNet 50. ResNet 50 belongs to the ResNet residual network family, known for introducing skip connections or residual connections. These connections allow the network to bypass some layers, mitigating the vanishing gradient problem. ResNet 50 specifically has 50 layers and is highly effective in capturing intricate features. EfficientNetBO. EfficientNetBO is part of the EfficientNet family, known for its compound scaling method that balances depth, width, and resolution. This architecture achieves impressive performance with fewer parameters, making it computationally efficient while maintaining accuracy. EfficientNetB3 with fully connected layers. The EfficientNetB3 model, augmented with fully connected layers, allows for fine-tuning and customization. These additional layers might adapt the network's learned features to the specific task of leukemia white blood cell classification, potentially improving performance. We can further enhance the performance by exploring other techniques such as YOLO V5 and YOLO V8 for detection of disease. YOLO, you only look once. Models like YOLO V5 and YOLO V8 are primarily designed for object detection tasks. They excel in detecting and localizing objects within images by dividing the image into a grid and predicting bounding boxes and class probabilities. In the context of disease detection in medical images, these models can potentially locate and identify leukemia white blood cells within the images. Comparison graph. This is the accuracy comparison graph. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions. True positives plus false positives. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have the FN score, and on the y-axis, we have the algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html and more, which represent different pages of the website. This is the dataset folder. In this folder, we are having test set and the train set. In the train set, we are having 2 classes, namely absent and present. In the absent folder, we are having the images which do not contain leukemia. And in the present folder, we are having the images which contain leukemia. So using the train set, we will train the models, and using the test set, we will evaluate the model's performance on the unseen data. In the test set, we are having 2 classes, namely absent and present. In the absent folder, we are having the images which do not contain leukemia, and in the present folder, we are having the images which contain leukemia. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are notebook.ipynb files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. This is the model file which contains algorithm information which will be loaded into the project code during runtime. First, we need to copy the path of the code folder from the address bar of the file explorer. I am copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. Here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally. Add the default address, which is the localhost this, and port, which is this. Now copy this local link provided by the Flask framework. I am copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up. So here we need to enter all these details to register. But I have already registered, so click on login. So here we need to enter the username and the password which we have created and then click on submit. We have logged in successfully. So here we need to upload the image, and after uploading the image we will predict whether the person is having leukemia or not. So click on choose file. Now click on upload. So here this is the uploaded image and the result is all absent. It means the person is not having leukemia. Now let us upload some more images. So click on try again and click on choose file to upload the image. On upload. So here we can see this is the uploaded image and it is predicted as all present. It means the person is infected by leukemia. So in this way, by uploading the image, we can predict whether the person is having leukemia or not. Now click on sign out. The conclusion of the project is the proposed model based on the EfficientNetB3 architecture with Depthwise separable convolutions demonstrates superior performance compared to existing benchmark deep learning and ensemble classifiers. This superiority is observed in the model's ability to accurately classify acute lymphoblastic leukemia ALL cells within white blood cell images. It potentially achieves higher accuracy, better precision recall, and overall F1 score when compared to these existing classifiers. Despite its enhanced performance, the proposed model maintains efficiency by utilizing fewer trainable parameters. This efficiency means it achieves accurate classification results while keeping the model relatively lightweight. Fewer parameters often imply faster computations, reduced memory requirements, and quicker inference times, which are highly valuable in practical applications. The proposed model's effectiveness is evaluated using various measures such as accuracy, precision, recall, and FN score. Accuracy is the ratio of correctly predicted cases to the total cases. Precision is the proportion of correctly identified positive cases out of all predicted positive cases. Recall is the proportion of correctly identified positive cases out of all actual positive cases. FN score is the harmonic mean of precision and recall, providing a balance between the two. These evaluation metrics collectively confirm that the proposed model performs well across multiple criteria, showcasing its ability to achieve accurate and reliable leukemia cell classification. Based on the findings and performance evaluation, the proposed model is deemed reliable for application in clinical research and by medical practitioners for leukemia detection purposes. Its accuracy, efficiency, and reliability make it a valuable tool for aiding medical professionals in diagnosing leukemia. Its potential use in clinical settings suggests it could contribute to more efficient and accurate diagnosis and subsequent treatment decisions for patients.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.